Uttarakhand. He has authored and co-authored more than 150 peer-reviewed international journals and conference papers. His research interests include the design of microwave filters, antennas, and absorbers for wireless communication systems. Now I request Dr. Akhilesh Mohan sir to start the session. Over to you,
Okay.
sir.
Okay. Thank you, Vikram. Okay. So I will share my screen. Let me share. Okay. Is my screen visible?
Yes, sir, it is visible.
Okay. Thank you, Vikram, for the for inviting me for this talk. So today I will focus on the high frequency antenna system for future generation wireless networks. As you told you, the main motive behind your main aim of your talk is 5G and 6G antennas. So I will discuss in the next 1.5 hours about the some 5G and 6G antennas, especially MIMO antennas, because that is it has been asked for to me to they will talk on MIMO antenna. Okay, now let's go further. So let me, the outline of my presentation. First, I will discuss the wireless communication in 5G and 6G network. Then after, what are the technologies options available for realizing antennas for their 5G or 6G. Then I will discuss the introduction to SIW technology, that is integrated waveguide technology. Then I will show some components and antennas, and as in 5G and 6G, the reconfigurable intelligent surface walls are going to come up in a big way. So I will discuss that one, and finally I will conclude my talk. So in wireless communication 5G network, so if you see the different wireless scenarios are there for sub-6. So basically, the in 5G network we have two types of two frequency bands are used for communication. First is FR1, and another is FR2. FR1 is your sub-6 gigahertz. The frequencies from 400 to 700, 7,000 some megahertz. It is called sub-6 gigahertz or extended sub-6 gigahertz. So that is used for long distance communication, But for high data rate, so we use the millimeter wave, that is called FR2 band, or any for backhaul, the millimeter waves are being used. So what we can say that in 5G network, we have both the microwave and the millimeter wave bands, so which will be used for the communication. Okay, now so we have the what are the frequency bands in the 5G network? So it is 5G NR, that is 5G new radio. So the consortium, that 3GPP, has assigned a lot of bands. They have given several bands starting from NR1, NR2, that is new radio 1, 2, 3. So they have given several bands. So the frequencies, as I told you, the frequencies are the FR1 from 410 to 7.125 gigahertz. This frequency band is FR1, that is for microwave, and for millimeter wave, 24 to 52 gigahertz is being used for the communication in the 5G network they are planning to use. Now, as I told you earlier, they have divided into the numerous bands, that is starting from NR1 to NR95. Each band has been designated as certain uplink frequency, downlink frequency, and the mode of operation, whether it will be FDD, that is frequency diplexing, frequency time, or time domain we will use. Now another is the FR2 band. So there 4 bands are there which are used for the communication. Now the 5G enabler. So as we have talked about the frequencies of 5G, that is FR1 and FR2. So now what is going to enable? So as we know that we will be having a large amount of data rate in the 5G and 6G. So we cannot use the microwave frequencies or normal communication technology. So we will be using there's a massive MIMO and beam forming techniques to point our beam in a particular direction, and for enhanced data rates and lower latency. So this I will just show you a comparison of frequencies. So it started long back from 2G, then 3G. So 2G is 3G, 4G, 5G, and 6G. So now 6G they have proposed till means in 6G they have proposed till terahertz. They are planning sub terahertz. They are planning to use. So yeah, so what it can be concluded from this slide that ultra high frequency, that is millimeter wave and terahertz or sub terahertz, will be used for future 6G communication for real time application. Now, so what are the antennas which are deployed in the 1G, 2G? In 1G, we have very simple antenna, that is was omnidirectional antenna. In 2G, we have single polarized antenna, but it was directional. In 5G, we have the dual polarized antenna. And in 4G, so we have the MIMO antenna, that is MIMO antenna, in which the antenna elements are from 2 to 8. In 5G, we have the massive MIMO, that is the antenna elements are 64 to 128. And in 6G, we have the ultra massive MIMO antennas where we have the 256 to 124 antennas elements will be deployed for high data rate communication. So 6G, so they have given the broadband, ubiquitous, and smart. Now, as can be seen here, that if you compare the data rate of 5G and 6G, so 5G, whatever the peak data rate is, your 1.01 Tbps, that is terabits per second. But in the 6G, it will be 1 Tbps, 100 times. And delay also, if you see, the delay is also reduced by 1/10. Now, reliability is also increased. Now, so what happens? So in 5G, we have 100 devices which are connected in a 100 meter square. But in 6G, we have the 1000 which will be connected in the same space. Now, what we can say that ultra high frequency and ultra large scale MIMO are the key technologies which will be used for the future coming 6G technology. Now, apart from that, so what can enable? So if you see here, so in the 5G and 6G, so these are some of the applications. So the peak data rate, as I told you earlier, also the services application is virtual reality or the augmented reality. So, and here it is using the massive MIMO, and maximum frequency it can use the 90 gigahertz. But for the 6G, it is using the RIS, that is reconfigurable intelligent surface, and maximum frequency 10 terahertz can be used. Now for 6G technology, so okay, so what are the applications? So applications of 5G to 6G are the metaverse, automatic car driven, the automatic self-driving car, or ADAS is there, automatic driving assistance systems are there. So there we require low latency and very high data rate, because it is a real time, you are monitoring in the real time, and intelligent manufacturing. Then medical, robot can or doctor can do surgery because the latency is very less. So it will be just a real time network UAV and smart cities. These are some of the applications of the. These are some of the applications of the 5G, that is 6G communication systems. Now, what are the technologies options available for realizing this type of antennas for 6G or 5G? So for 2D, if you see, the two-dimensional technologies are there, that is two-dimensional, that are planar technologies. We have microstrip line and the CPW. So what are the advantages of this 2D? They are compact, low profile, lightweight components can be designed, and they require inexpensive fabrication technology. But the disadvantage are they have the significant losses, especially if we talk about at higher frequencies, and they have radiation leakage because the structures are open. And due to the radiation leakage, they have the undesired coupling between the adjacent element, and they have the limited power handling capability because of the dielectric material, because every dielectric material is having certain background voltage. So they have the limited power handling capability. Now, the 3D technology, so that is, they are waveguides basically. So they have the advantage of 3D technology are low losses, good quality factor, and high power levels. So it means they can handle large amount of power and good quality factor. The components which is having the good quality factor components can be designed using this type of technology. But the disadvantage is they are bulky in nature. They require expensive fabrication machinery, and the transitions are required because they have to connect to the planar circuit. So we require transitions are required. Now, researchers has thought that why can't we combine in 2000, near about 2000, combine the combined the advantages of 2D and 3D technologies, and they have come up with a new type of technology called SIW, substrate indicated waveguide technology. It is a planar form of a rectangular waveguide, where the top and bottom walls of a rectangular waveguide are similar as the copper cladding of copper cladding of that is of a PCB, and the side walls are realized by a series of metallic vias. So it is just a planar form of a rectangular waveguide. So its performance will be in between 2D and 3D, that is between the microstrip line and the advanced in between and the waveguides. Now the introduction to SIW technology. So it history lies back, long back, as I told you, that is maybe 30 years back in 1994. So the Japanese group has, that is, they have given a name waveguide line and different types of laminated waveguide, and they have proposed this one, but no work has been done because they have just proposed it, because you know that for transmission line, if you are to use the transmission line for designing any component, you require its Z naught and the beta, that is Z naught and gamma, that is characteristic impedance and the propagation constant gamma. So now in 2002 or near about, the Q and Desland has and some in the Royal Military College Canada. So they have studied this type of transmission line, and they have come up with the characteristic impedance, propagation constant, that is phase constant, and the law attenuations, and then the components are being designed using this type of technology. So yeah, then the components are being designed. So here, these are what are the design parameters? Some of the design parameters of the SIW technology is the width of the waveguide. The width of the waveguide, as you know, in any waveguide, the width decides the cutoff frequency, because they support the TE10 mode, that is dominant mode. So it is related to the cutoff frequency. If you want to have lower cutoff frequency, then width should be larger, and so on. And the diameter D should be as a fractional of W, generally fraction of W, such that there is no and the longitudinal spacing S, that is the spacing between the two VRs or the VRs should be S. The ideally should be S equals to 2D, that is you have continuous series of VRs with no gaps, but typical choice is 2D. It has been shown experimentally or through the simulations that if we choose S equals 2D, then what we can have, there will be a confinement of electromagnetic energy inside the waveguide. There won't be any leakage from the out in the other part of your transmission line. So it behaves like a waveguide, rectangular waveguide. Now, one main thing is that for certain application, for leaky wave antenna, we intentionally choose S larger than 2D because we design the leaky wave antenna. Leaky wave antennas, the principle of leaky antenna, they are called traveling wave antenna. They are not resonant wave antenna. So as the wave travels and it leaks from the side walls, and as the wave travels, it leaks from the side walls, and you have the radiations, and you will get it will radiate, and it behaves like an antenna. Okay, now the SIW, as I told you, the dominant mode is TE10 mode. It doesn't support TM mode. Why? The reason behind it doesn't support TM mode, and TM mode is that because the side walls for TM mode, we require the continuity of current across the side walls, means across the VRs. So that is why it doesn't support the TM mode. It only supports the TE mode. And the rectangle and the formulas are similar, whatever the waveguide we have. So it is just similar to the rectangular waveguide. But there is a slight change. Slight change is that because of the introduction of this VRs, so what we will have, the VR, so we will have effective width or effective width. So effective width can be found out by this equation. So the effective, because of the presence of, let's say if it is perfect wall, then we have just effective width will be W, plus because of the VRs. So if it is having the effective width, which will be substituted in the to calculate the resonant frequency of this one. And so now the question comes, so what are the values of S and D? So generally the region of interest here, it is shown that, so if you choose S, how the S and D are linked to the lambda. So if we choose the region of interest that is blue in color or green in color, which is showing here, so that will be, so you will have the faithful, that is, so the electromagnetic wave will propagate inside the waveguide. Otherwise, there will be leakage or maybe some stop band will be formed. So it is not practically possible. That is, so we will not have faithful or the successful transmission of electromagnetic wave from the waveguide. Now, as I told you the earlier, so we have the Desland and this one, so they have come up with the that is propagation constant, characteristic impedance, and this one. So after the in 2002, after that you can see lot of works which has been done for the means this SIW is being used for the design of electromagnetic components. They have designed filters, oscillators, amplifiers, numerous circuits they have designed using the SIW technology. So this is just a comparison of all the structures. So it is it is inferior to metallic and the coaxial line, but better, that is but better than the strip line, micro strip line, and coplanar waveguide. So it is just a planar form of a rectangular waveguide, as I told you earlier. So now people have designed the entire transmitter using a SIW technology. They have designed antenna array using the SIW technology. So they have designed the filters using SIW technology, couplers, and they have used in amplifiers, they have used, or maybe in oscillators they have used. So they have used the SIW technology. So SIW is a prominent technology and it can be used for the design of all passive components, or it can be used for partly in the design of the active component. So advantages, as I told you earlier, so the power handling are higher compared to the microstrip line. Low losses are there, and due to the shielding, because it is a closed structure and it is low profile. But the limitations are, again, it will have the dielectric loss and leakage. Also, leakage loss is there if you are not able to apply the condition as opposed to 2D. And due to its waveguide nature, it is also have the cutoff frequency. So it cannot be starting from the zero, that is TEM mode, 0 to infinity. It has a certain cutoff frequency. You can operate it after certain frequency then. Okay. Now, so here's are some of the components which our group has designed: some planar antennas, 3D antennas, and some filters using the SIW technology which has been designed. Now come to the rectangular waveguide technology. In the rectangular waveguide SIW cavity, so here I have shown you the rectangular SIW cavity. So we have studied the, I have shown you the SIW. Now in SIW, SIW, that is substituted waveguide. In the waveguide, if you cover the back and the front portion, then the cavity will be formed. Here it is shown. So the back and the front and the back is covered, so the cavity will be formed. So it will be a rectangular SIW cavity. It will be just equivalent rectangle, as I told you earlier, equivalent cavity with certain change in the L effective and W effective, that because of the presence of the vias. So the resonant frequency of this one will be Fm and P will be this given by this. That is 1 by 2 pi mu epsilon, and this formula, this standard formula of any resonant cavity. Now feeding method. Now, once you have studied the cavity, so cavity has certain modes, different modes are there. So now we have to excite the particular different modes inside the cavity. So there are different types of feeding mechanism. Feeding mechanism is used to, basically we connect the microstrip line to match the fields of the microstrip line to the this one, such that there will be less reflection in the sidewall. So here, because here, let's say here impedance is there is 50 ohm. Here the impedance is 120 or 100 ohms, not 100. So it will have waveguide. So they will have some match. So the taper transition is being used for the matching. Another will be the current probe is there. So the different types of matching is there. So their matching is used to launch the electromagnetic power. Now so it is another way, the right-handed 90-degree bend. So it is CPW feed type of their structure. So they use the 90-degree bends here to match the impedance here. Now other feeding mechanism. So depending upon the requirement, you apply the feed. Basically, the main aim is that so you have to study the modes and study the feeding mechanism such that the particular mode is launched inside the waveguide. Let us say that if you see here, so here maybe some mode is long, some mode will be excited, but here it will not be getting excited. So there are different types of feeding mechanism are being used. Now, what are the modes of this SIW cavity? So this is your square SIW cavity. So that is TEMN0 or MNP. So M denotes the number of half wavelength variation in the x direction. N denotes the number of half wavelength variations along the y direction, and P denotes across the z direction. So here TE110 means, so let's say if I say this is x, So in the X direction, they have one half wavelength variation. In the Y also, they have one half wavelength. And for Z, we have written 0. That is TE110. 110 means there is no variation of electromagnetic field across the Z direction. It is constant. So this is the 2D or top view, and this is the 3D view. So this is the TE110, TE210, 12220. So these are the modes. So you can observe the fields. So 110 is having all the fields are upward, and 210 half of will be upward, half downward, and 210 is this one, and similarly 220 also will have the similar field. Now SIW is slot antenna. Now what is that? So what is a slot antenna? A slot antenna is just a metal surface. It is a flat surface. If you cut any hole or a slot in the slot, cut out, so and you feed that slot, then it will likely to radiate the electromagnetic. So it will likely to radiate. So main thing is that you have to feed the slot. So it will have the similar characteristics or similar radiation pattern as of the dipole due to because of the Babinet principle. Babinet principle. So I'm not discussing here Babinet principle. So in Babinet principle, what we show that so the slot antenna behaves similar as a dipole antenna, and the frequency and the radiation pattern depends on the size and shape of the slot. Okay, so now the main advantage of this slot is dipole is your two-dimensional structure and slot is your planar structure. So you can use the planar structure, or you can just have the simpler in the planar structure. You can do that. Now, so now the cavity backed slot antenna. In the cavity backed slot antenna, so as you know, so if what is the radiation pattern of a dipole? The dipole radiation pattern is omnidirectional. Now, since for certain application, for most of the application, we require directional antenna. So how to make it directional antenna? We put the reflector at the back of the dipole. So similarly, we put a reflector, or we make a cavity that is called cavity backed slot antenna. So here, if you can see, it can be so it is cavity back. So this cavity will reflect the one sides of radiation and increase the directivity or gain of the antenna. So this will be this one, cavity backed slot antenna. So its radiation efficiency is high. It have high to front to back ratio and high isolation from the environment. The properties of this one. Now, if you use the similar thing into the SIW technology, so this is okay. This is vias we have, and they are the rectangular. So it will be also the cavity backed slot antenna. So it is low profile, cost effective, simple integration, and ease of with the planar circuits will be there. Okay, now as I told you earlier, so the cavity backed slot antenna. So main thing is that you have to have excitation. So you have to have feed. So you can see here it is coaxial feed, which is excited at the center. It is something like it is the tap feed or inset feed, which is here. Again, it is coaxial feed. So you can, and these feeds are related to the what are the particular modes you want to excite. And the slot also, slot can take any shape or size depending upon what you want to radiate, what mode you want to radiate. So here they have the rectangular slot, here interdistal slot, here cross-shaped slots. So there are different types of antennas can be designed. Each one will have distinct characteristics. Now, these are the design flow chart of the cavity backed slot antenna. So what is that? First, choose a SIW cavity. So let's say I have discussed here rectangular SIW cavity, square SIW cavity. You can thought of any SIW. You can thought of circular SIW cavity, elliptical, any shape you can think of. I mean, think it should be planar. So and then study the modes of what are the modes this SIW cavity supports. I have shown you some of the modes of the square SIW cavity, TE110, TE120, 210, and T220. Similarly, you can think of the circular SIW cavity. It will support also different modes will be there. Now, study the modes. What are the modes the structure cavity supports? Then after that, what do? You apply the feed, because apply the feed to excite a particular mode. Let's say I want to use, I want to design an antenna at X 10 gigahertz. So this particular mode is resulting at 10 gigahertz. Then you have to excite this 10 gigahertz mode. Okay, the feed such a way that it will excite. Then after that, you introduce a radiating slot. Radiating slots are introduced such that the particular mode is likely to radiate. So it will radiate if you introduce, and after that you optimize the slot, the dimension for bandwidth and polarization slide, and fabricate it and measure the characteristics, and finally you will verify your entire cavity bagged slot antenna will be designed. This is very simple. Just I will show you here. So this is the cavity bagged slot antenna. First one. So here it is a SIW cavity where it is having the TE110 mode. In TE110 mode, the fields are like this. So the fields are means as I shown you here, the fields are at the center here. Okay, T1 at the center fields are. Now, if I introduce a slot here at the center, it will not radiate. If I introduce a rectangular slot, it will not radiate. But if I, why? Because you know in this slot, the electric field is built up. And since the electric field is built up, if you see the sides of the slot, so it is having the equipotential. The equipotential will be there, so there won't be any electric field will be there. It will not radiate. Now, if you switch the slot from center, exactly center to some offset distance, then it will radiate. So that is why they have shown you here. They have shown it is not exactly at the center, it is somewhat offset. So it will likely to radiate. So it will radiate. So simple TE110 mode, they got the bandwidth of 1.7%. Now further, they have combined two modes, 110 and 210. So I will explain how we can combine. So if I 110 and 210. Now if I, as I told you, so for T110, we have introduced a slot here. For T120 mode, if you introduce a slot here, so then it will radiate, but this mode will not radiate. But this, okay. One more thing also. So if you see observe this I have drawn for the this for the duroid, that is 2.2, and the thickness this one, and cavity size is A cross A, that 15 cross 15. The resonant frequencies are 7.45, 11.75, 11.75, and 14.85. Now, if I choose the rectangular SIW cavity instead of having the square SIW cavity, then what is going to happen? This second mode is going to coming closer to the first one, this one. So the mode will be coming closer to each other. Then the modes can be merged to design the wideband antenna. So now if you again introduce a slot here at the slight offset location, so these two modes will combine and will likely to radiate and get the wideband characteristics. So here, so the fractional bandwidth of 1.7, and now it has improved to 6.3 because they have used the two frequencies, that is two modes, TE110 and 120 modes, combined these two, and the bandwidth has been improved. After this, so what you can think of, similarly, if you etch a butterfly shaped slot, so butterfly generally the slot length are lambda by 2 at the center frequency. Now the butterfly shaped structures are popular for their wideband characteristic. Means you can think of it is just a you can think of just a slots of different dimensions which are there. So it is having the wideband characteristics. So the people have etched the slots here at the top to get the wideband characteristics. So here the bandwidth has been increased to the 9.4%. Now the question comes. So we have the SIW, we have the SIW antennas we have designed. Now we will design the SIW MIMO antenna. If you have any questions, you can ask me. I will try to answer, or I can progress further. No questions. Okay. Then I will move further. Yeah. So what is the difference between VIA and SIW? No, VIA is just a VIA is just this one. You can say this wire or whatever this structures are called VIAs. And SIW is substrate indicate waveguide. Entire waveguide is there. So this is your SIW. So what I can tell you, this is your SIW, that is substrate integrated waveguide. So this is, so in waveguide, if you might have seen or studied the rectangular waveguide. So the electromagnetic energy flows into the waveguide. So it is just a formation of rectangular waveguide. So this is the difference between the SIW. In SIW, vias are being used. These metallic portions are called vias, which are used for the design to make a side walls. These vias are being used. Okay. So then I will move further. So SIW MIMO antennas. So we have discussed different types of SIW antennas, SIW slot antennas. Now they can be used for the SIW MIMO antenna. Just same. So they have means basically the simplest MIMO is that you should have a common ground plane. Common ground plane is there. So common ground plane, and so they have kept few slot antennas side by side, and they got the SIW MIMO antenna. Now question is there. So because of, as there is some leakage or there will be some interaction of electromagnetic fields between the one port and the another one, so there will be isolation will be poor. So what is the concept of MIMO? Concept of MIMO is that you can enhance the cavity such that if you have n channel, n, that is n cross n MIMO, that, or let's say 2 cross 2 or 4 cross 4 MIMO, 4 distinct radiations uncorrelated channels will be formed. So uncorrelated channel will be formed. So for uncorrelated channel, so you must have the good isolation. So for good isolation, what happens? So since this SIW radiates at one single frequency, they have applied some type of a structure, so which can give it is something like some band gap structure or DGS structure, such that whatever the electromagnetic energy should radiate only in this direction. It won't come to the near one. So in such a way, the good isolation can be obtained. So they have shown here. It is basically in there. It is basically in the walls. They have applied certain vias and transitions. So such that they choose the frequency such that it lies in the band gap of this structure. This is periodic structure, mushroom shape structure, such that they have the band gap will be formed during that frequency, and there won't be any. So basically, the frequencies will be attenuated, and it won't reach here. So good isolation will be obtained. So here, if you can observe from here, they have obtained the isolation better than 42 dB. 42 dB is very good isolation. So this is structure. So they have obtained. Now, second structure. So since it is a 3D structure, so it is not practically possible to deploy the 3D structure. So they have come up with the planar version of it. So instead of having this one, so they have applied the mushroom shape structure here itself in the ground plane. The mushroom like loading is there. So they have, at least they have they got somewhat poor isolation, but it is a planar structure. So they have the isolation near about 35 dB. But near about 35 dB they have, because now, but it is a planar structure. Now another one, what they did means in another structure they have, since it is a full mode structure. Full mode structure means they are using the TE110 mode. So now as the resonance frequency depends on the length of the slot, so you cannot increase the length of the slot. So what they made it somewhat tapered like this. So the frequency has been lowered down. That is semi-tapered slot are being introduced, and they got the some isolations are poor. So that is better than 24 dB, not very good as compared to the earlier one. So these are some of the MIMO slot antennas. As I told you earlier, in the 5G and the 6G technologies, we have the massive MIMO and ultra massive MIMO. So if we use this type of antennas, it is not practically possible to deploy, or the size will be very large, because you have to deploy, that is 64 antennas, or maybe more than that for 254 or the massive, ultra massive MIMO. So for that, we need miniaturized antennas. So that is, we will discuss SIW miniaturized antennas. So what is going to happen? So that is miniaturized antenna. So this is your full SIW cavity, full mode. So I have shown you the square cavity or the rectangular cavity. It is a circular SIW cavity. So here it is having some mode, just nomenclature of some mode is there. So if you see this mode is radially symmetric along the that is phi direction. Now, if I apply the magnetic wall concept, there is a concept called magnetic wall. If the fields are symmetrical, you can apply the magnetic wall concept or make it open circuit. Then what happens? The component will behave similar as that of the same one. So this is a full mode SIW cavity, FM SIW cavity. If I apply bifurcate into two equal halves, the size will be reduced to half. This is called HM SIW cavity, half mode SIW cavity. Its resonant frequency will be similar to this one, near about a slight change. Just let's say if it is in 2.4, it will be 2.45, something like that, but nearly same, and it will have the similar field characteristics. Now, further, if you apply the magnetic wall concept here across this one, because the field, so you can apply magnetic wall concept infinitely as soon as the fields are symmetrical. So since the fields are symmetrical here, so you can apply this. So we got the quarter mode SIW cavity, that is called QM SIW cavity. Further, you apply the magnetic wall concept here, so you'll get 8th mode, you get 16th mode. So this, we can say that this HMSIW quarter mode, that QMSIW 8th mode, SM 16th mode can be used because the size of the frequencies are nearby, characteristics are similar, characteristics are more or less, because the modal characteristics are preserved in the by applying the magnetic wall concept. So they can be used for the design of miniaturized microwave component or miniaturized SIW antennas. So this is I have discussed. So similar thing can be thought of the square SIW cavity. So this is our full mode SIW cavity. If I bifurcate along the line direction I have shown here, so we got the HMSIW, that is half mode. Further, if you bifurcate along this one, so you got quarter mode. And further, if you bifurcate along the diagonal, you will get 8th mode. Similarly, I don't want, instead of I will bifurcate along the diagonal, so I will get, this is also called HMSIW, the diagonal HMSIW, then quarter mode along this one, and these will be used for the design of microwave components. So now if we can see from here, the size reduction in 16th mode is 93%, and the quality factor, if you see, the quality factor doesn't change. The quality factor earlier was maybe not doesn't change, it will be slight inferior to that, but the price, that is means you are getting huge advantage of reduced means of the reduced size that can be deployed for the any handheld component. Now, so this is, people have designed the square QMSIW cavity. So here the square SIW cavity was there, so they have fit from here, so they got the one, they have designed the antenna. So here they have designed a dual band antenna. The first mode is because of the first band is because of the TE11 dominant mode, TE110. Second band is because of the TE220 mode. This is they have shown. Now in the circular SIW cavity, so this they have designed the circular SIW cavity, that is a quarter mode antenna. This is your 16th mode antenna, and so on. People have designed, lots of work has been done. Now, so these are some miniaturized version of the SIW antennas. They can be used for the design of the MIMO antennas or whatever the massive MIMO. So now miniaturized SIW MIMO antennas. So how we can design? So whatever we have discussed here earlier, that is miniaturized SIW antennas, can be used for the design of MIMO antenna as an antenna element. So now, so the square SIW cavity, that is with a square SIW MIMO antenna. So they brought to a square SIW cavity, not a square QM SIW, and they have applied some isolation. The principle is very simple. Just you have to separate radiators, antenna 1, antenna 2, brought them closer to each other, and apply certain mechanism to enhance the isolation. Because we require an isolation better than 15 dB or 20 dB for faithful MIMO performance or good MIMO performance. So that is very simple principle is there. So they have deployed some T-shaped slots. So they have so it was 2x2 MIMO antenna. That was 5G application. They have now this is 4x4. Just they have missed 4x4. They have similarly, so they can increase the number. So now they have used the 8th mode. Earlier it was quarter mode. Now 8th mode again. So they have applied certain slot type of structure to get the isolation. Here they have especially placed, means they are placed such as their isolation is good. This is also quarter eighth mode structure is there. MIMO antenna. Then they have they want to reduce the size. They have applied means they have chosen in such a way that edges are closer to each other. So it is square eighth mode and circular eighth mode they have designed. The principle remains same. So you can design, that is they have designed the two, that is they have designed the 2-port antenna, that is 2-port MIMO antenna using a circular eighth mode SAW cavity, and similarly 4-port. Here they have not applied anything for mechanism, but for the 4-port they have applied the some structure for to enhance the mechanism. And similarly for the 12 cross, that is 12-port beam antenna for the mobile applications they have designed. Main thing is that you have to deploy the antennas as required and apply the isolation enhancement techniques. Okay, now so these are the some of the SIW MIMO miniaturized SIW MIMO antenna designs. So what I have shown, the principle is same. Bring two resonators closer, radiator closer to each other, apply the isolation techniques to get the good isolation. That is anything better than 15 dB or 20 dB is a good isolation. Now, so okay, now as I told you for mobile, as I told you earlier, so for 5G applications, 5G new radio applications, so what we have, we want to have the communication for 5G and for the microwave and the millimeter wave. So that is, so here I will present a that is integrated dual 8-port MIMO antenna for sub-6 GHz and millimeter wave, because in the because you can have separate antennas in the base station, but for the in the mobile you will have the same thing. You will have the antennas for both sub-6 GHz and the millimeter wave also. So that is why if you see in the some of the mobile phone application, they are especially saying because the 4G we don't have millimeter wave communication, but in 5G we have the microwave and the millimeter wave communication. So that is why it is 5G phone they are saying. So they have the millimeter wave communication also. So now, so as I've already discussed this one, this is the bifurcation property. So what we did here, so if you observe here, so we made two cavities, that is two cavities here. So two types of cavities are there. That is two types of cavities. So outer cavity is for the microwave and inner cavity is for the millimeter wave. Outer cavity means in outer cavity what we have deployed different types of QMSIW structures. So here something like square and this diagonal. So I have shown you here. So this QMSIW structures are there. So here they are being used for the microwave, and for millimeter wave again the same thing, it is being used. But for millimeter wave, as you know, the millimeter wave the frequency is higher, size will be lesser, size will be smaller. So they have deployed. So they have used higher order modes for the to design the higher order hybrid modes for the design of this millimeter wave components. So they have used this one that is TE330 mode for the higher order modes are there. Just I will show you know, just to show you here. Okay, just I will move to the okay. So now also, so SIW. Okay, I will move to the so SIW part is over. If you have any questions, you can ask me. Then I will move to the RIS part. Okay, then then I will move to the RIS part, or SIW slot antennas for IoT application. So you know, in the near future, IoTs are coming in a big way, that Internet of Things. So everywhere we will have the deploy the antennas or the antenna, the Internet of Things, because the devices will be communicating through each other. Now question comes, what type of antennas we can use? So it is for smart antenna, not a smart, the green antennas you can think of. Green antenna, that is which is biodegradable, it should be there. So what happens? So people have designed using the simpler substances which are available They have not used any dielectric material. So they have used the copper plated something like some conductive layer. some the fabrics are, it is basically fabrics are being used. And instead of for the vias, they have used brass tubulars. Eyelets are there, so they have used. So they have designed on the cork. Means let's say they have designed on the paper. The paper substrate they have used. You can use fabric. You can use cork. You can, all materials are biodegradable. They can be used. So if you think of, you can think of your own, any, choose any biodegradable material, and you design the whatever the SW antennas and try to design it. Okay. So now main thing is that you have to characterize the substrate. Characterize the substrate means you have to characterize. How do you characterize? So let's say I will design on any wood. So, but I don't know the dielectric constant of the wood or any material, let's say. So you have to find out the epsilon r tan delta of the material. For that, there are different methods are there. That is Nicholson, Ross, Wiener method is there, and RW method is there. So where you form a cavity, just place the material there and try to find out the extract the epsilon r and tan delta from of that material. Then you can use it for the design or in the CST or in HFSS. Okay, so and also, so let us say that if you used for the variable antennas, so you have to study the its curvature property, means how does the antenna performance get changed if it is performed on the curvature, means it applied on the in body net. Okay, okay, I will move to the, I will stop here and I will move to the this RIS, intelligent introduction to intelligent reconfigurable intelligent surface, that is RIS. So what is that? I will discuss here. So if you know, if you have studied the electromagnetics, if you know the phase propagation formula, if you have a transmitter, okay, if you have a transmitter, then okay, if you have a transmitter, then you can observe that at 1 meter, what you will have, you will get let's say if you will get only 0.005% of power. Now, if you, let's say if you move to 10 meter, you will get much lesser. So what I want to show, I want to say from here, that only a tiny fraction of power is received here. Means let's say if your antenna is radiating, how much power we are, let's say how much power we are getting in the mobile from the transmitter. Let's say if your base station is radiating few watts, you are getting few nanowatts. That is 1 billion time, few nanowatts you are getting. And during communication, it will be microwatt. Microwatt, then it will be, let's say, 1 into 10 to the power minus 6 times of the whatever has been transmitted from the base station. So what happens, as you know, as the number of as what we want large data to be transmitted. So what happens? So what we want? So now, if we are sitting inside the room, so again we are already having the lesser, that is minus 43, minus 63. We are sitting inside the room, then minus 20 dB extra. And other than that, we have the we have the reflections, scattering, and diffractions. Reflection is scattering, reflections from the walls, any metallic objects, then scattering from any uneven surface, and diffraction from any sharp objects are there. So what you are getting minus how much? You are getting minus 83, 87 dB of power at your mobile, this one. So that is not suitable. So you will not have any faithful communication. So what people have thought, that why can't we apply the we can shape the signal, which is what we are. So what, let's see, if the transmitter is there. So this is the structure whatever we have. So we apply certain curtains or certain structures here, such a way what we will have good amount of power, which we are getting inside the room or anywhere else. So that is called, so what these structures are called, reconfigurable intelligent surface, that is called RIS. Reconfigurable means properties can be changed or altered. So it is not just like it is just a simple screen, a pattern is there, and intelligent means it is real time, and surface is two-dimensional, scatter surface is there, so it is called surface. Now, if you have, so what you have, it is basically just a patches are there. So, but patches, just not simple patches are there. So they are, I will discuss. So they basically, patches are programmed in such a way. So whatever the signal you are getting, they are trying to reshape, not shape. They are trying to reshape in a particular direction, or move, means orient towards the particular direction. So here, so if one element is there, so each in a, so here you can observe it will have numerous elements. Just lots of bits of elements are there, and you have to control with a programmer controller, that is by FPGA, to control. Now what you can change, the frequency cannot be changed, because just what we change the phase. We change the phase of the signal by just changing the phase of signal. So it will be oriented towards the direction that we will see. Now one element cannot change, but if you have a group of element, it can be changed. Okay. Now what is, so now if you see, if you have a continuous surface, then what is going to happen? Then uh, what is going to happen? So it will have, so if you observe these lambda by 2, if the element here, okay, now continuous surface is not practically possible, because it is basically you are continuously changing the phase. It is not practically possible. Now what we, if you discretize this surface into number of discrete patches and change the phases, then it will be possible. Now if we choose lambda by 2, cross lambda by 2 patch size, then what happens? It will be having gain, normalized gain. That means whatever the signal it is arriving, it is being lost. Now if you further reduce that one, so it won't be lost, the magnitude won't be lost, it will be nearly, it will retain its mechanism. So you can see, observe from here, so it will have the normalized gain of nearly about 0 dB when it moves to the lower in size, that is when your patch size are smaller, that is lambda by 8. Okay. Now the reconfigurable world. So now RIS can be controlled. So you can, the blue you can see here. So that is, it can be used in the buildings, inside the buildings, outside the buildings, for to direct your signal in a particular direction, and to change the polarization, and for signal absorption. So that is, so what we'll see only the direction, how it can change the direction. It can protect you from eavesdropping. Somebody cannot listen you outside the room, and mitigate the shadow fading. So it was not like that RIS is coming just now. It was coming not long back, that is 1 decade back, but they have come up with different names. So that is, they have called it intelligent wall, software controlled meta surface, reconfigurable intelligent surface, then reconfigurable AI meta surface, and numerous names were there. But now people have narrowed down. Now they call it reconfigurable intelligent surface, that is RIS. Now, so the background of RIS, so RIS is just it composed large number of reconfigurable sub-wavelength elements. Sub-wavelength means elements. So that is lambda by less than lambda by 8. So now if you see the classical communication nowadays, what is happening? So what if transmitter is there? If you have a receiver, so now the receiver will get the signal because of some reflection, scattering, and diffraction. You'll get, and the signal whatever reaching here is very less. Now, if I apply the RIS, let's say on this wall on the building, then what happens? So it will, this signal, this RIS will focus this beam towards this particular direction, this particular RIS, and then receiver will get the good amount of signal. So what we can say, that this RIS can intelligently reconfigure the wireless environment. It is a potential key for the 6G, future coming 6G communication. 6G communication. Now, brief history of this RIS. So metamaterials already know. It is a meta means beyond, material means material substance. So that is, if something is not existing in nature, that is called metamaterial. That is, means you have metamaterial which have the unnatural. So what, to get this property? So what we, so you can these properties doesn't exist in nature. If and doesn't exist in nature, the metasurface is a two-dimensional equivalent of the metasurface. Metamaterials are three-dimensional. Metasurface is a two-dimensional equivalent to manipulate the signal. And so there are different types of metasurface are there. So basically what happens, the numerous patches are there, and you have to switch on and off or change the phases of the patches to manipulate the signal. So here, if you see here, that is the can be viewed as it is basically a reflective array composed of large number of programmable sub-wavelength components. So here array structure is there. So if you can program it, means program in such a way, if you choose certain biasing voltage or whatever the on and off of a structure, so your beam can be shifted from, that is from 0 degree plus 30 minus 60. The beam can be switched from one direction to another. It can be moved. So now, so the work has started from 2020, and people are deploying also in the China. They have deployed it. So they have in the China, Japan, and US. So they call it reconfigurable wall. They have reconfigurable paintings are there. The transmissive surface, meta surface are there. So they have demonstrated. In India also, we have demonstrated our group at here. Not our group, another professor in the communication, they have demonstrated the RIS surface, the practical demonstration at 2.4 gigahertz. Now, out of this RIS aided communication happens. So this RIS aided, so if you see the user is there. So the RIS is deployed on the wall. So another user is there. So you will have the good amount of, so RIS enhances the signal quality, increases the spectrum, and saves the power, increases the energy efficiency. Others I will discuss later on. So now if I compare the massive MIMO and the RIS, so because both of them are the future coming technology. So RIS, so both of them have the, so in massive MIMO, so massive MIMO, you have to, let's say if you have 256 antennas, so 256 uncorrelated channels has to be formed. So you have to have 256 transmitter and 256 receiver. So you require large amount of hardware. So if hardware is required, then you require large amount of power. So large amount of power is very high. But here we don't need anything. We just need some surface and some microcontroller. So it is basically you are redirecting or radiating the signal in the RIS. But here it is not like that. So here what we are having the RF chain, we are doing the baseband processing. The cost is very high. That is why people are planning to move from the massive MIMO to the RIS. It is a very key enabler feature technology for the 6G technology. This RIS is the, so okay. So now the concept of active RIS. So passive RIS, let's say okay, so you transmitter your RIS is there. So you are not just, it is just reflecting the signal without any amplification. So let's say I want to further amplify the signal, then I can use the active RIS. So at the back of this phase shifting element, so you can use some amplification process can be used to amplify the signal. So this active RIS can amplify the signal using power amplifier. So people have worked a lot on this one. So they have worked a lot on to design on the active reflection type power amplifier. Okay, now, so I will just show you some work which our group has designed. That is 2-bit tunable unit cell for quad band reconfigured antenna surface. So what we have designed, just to show you, so it is just a surface, just a unit cell is there, this one. So if the unit cell is there, so this unit cell is basically a patch is there, and in the patch you have the 4 U-shaped structures which are connected here through some strips are there. So now we have applied the vector diodes, 2 vector diodes. You can apply n number of, basically you have to change the phase of this one, or you have to change some characteristics of this one, this property, and VI is there. So now if I apply, or if I change the different states, if I different biasing voltage of this vector diode, my capacitance will change, because the vector diode works in the reverse bias condition. If you change the reverse bias voltage, the reverse bias capacitance changes and the frequency will change. So for that, if you change so we have taken the 16 different stages, so the frequency can be changed and phase also can be changed. So what we have plotted, so what different stages, so for first 4 stages, so it is working on that is 3.5. For another 4 stages, that is 5.1, another 4 So that is 5.85 and another, this is 8.4. So basically you have to study the amplitude, that is phase, and the magnitude characteristics. So okay, now based on that, so what are, how much phase? So we don't have any control over the amplitude because these are the passive. But we can have the control over the phase, as I told you, because in the reflective surface is there. So you can change the phase. So how to change the phase? By giving the bias voltage. So here here you can see the first graph. So we have the magnitude is more, the reflection magnitude is more or less same, but the phase is changing. Let's say if you talk about the phase at any particular frequency, one is having one phase, let's say 90 degree, another will have the 180 degree, or maybe some change in the phase will be there. So phase change can be obtained. So here we have plotted the magnitude change and the phase change. So you can observe the different phase characteristics for different. For different phase characteristics can be obtained. Once the different phase characteristics can be obtained, so this is shown you which this is just to show you the which part of it is responsible for which frequency. I think now then what after that you apply this structure. So you okay now. So let us say that for certain application I need a this type of, okay, no, this I will discuss later on. So now, so let us say that this is my reflective surface. I require a phase of 180 degree at the center, 270 at this one, 0 degree here, and so on. So that I can switch the beam. Now, if I apply, this is my surface. So my structure is will be somewhat like that. This is my RIS surface. This is my feed antenna. Feed antenna, I have chosen the broadband because since we have the broadband characteristics, we want to we want to switch the beam to the large number of frequencies. So we have taken the feed antenna. Here comb shaped feed and Vivaldi type of antenna is there. So now it can be observed that if you change the RIS, this one, that is 0 degree minus 20 degree and this one, so it can be, the beam can be shifted. So it is not shown in the lower frequency, it is visible at the higher frequency, that is at 5.7. If you see, if my beam can be shifted by just changing the whatever the code pattern what we have shown you earlier. So and also at 8.4 also you can shift your beam in a particular direction, that is from 0 degree, minus 20 degree, 80 degree. So you can shift your beam. This is for the one half, another half can be plus also can be shift. But main thing is that you have to, so here we have just shown, you have to understand how to shift this phase mechanism that is required. Okay, so I will stop here. So now if you have any questions, you can ask me, or anything you want to ask me, you can. Yeah.
Thank you, sir.
Thank you,
Thank you
Vikram.
for delivering such a special talk. Participants, if you have any doubt or query, you may ask on this chat box. So there are some participant doubt in the chat box. So one basic question.
Okay. Yeah.
Both the side slot will be visible. I am new to this SIW technique.
What is the question? Where? Which question? Okay. No,
So
this
this
first one,
second
Abhishek
last.
Karwa. Yeah, I
Second
will
last
take
question.
second last. Okay, the both the side slots will be visible. So I don't understand the question.
Yeah.
So basically, okay, just I will show you. Okay, so this is your SIW structure. So how does this SIW will look like? So it is PCB, that is printed circuit board. On the top, you have the copper, and on the bottom also you have the copper. Okay, on the top you have copper, on the bottom you have copper, and in between you have this is the wires, or we call it vias. So vias or host, different people, different names. We call it via. So vias these are the basically metals are there. Copper wires are there. These copper wires are there. So, and they are the value of W depends on the frequency you want, that is cutoff frequency of this waveguide, and the dimensions. This S equals to, and spacing between this the W is equals to 2D. That is two times of the diameter. That is, in between you have just a space of 1 diameter. So then there won't be any leakage of the electromagnetic energy from the side walls. If this S equals to, you can have, depending upon the application, not application, fabrication facility, you can choose, ideally it should be 2D. Ideally it should be 1D, it's equals to D, but we generally choose equals to 2D, then there won't be any leakage from the electromagnetic, this one. Otherwise, if you choose S equals to 3D or 4D, you will be having the electromagnetic power. There will be leakage from this one side walls. So leakage, what does it mean? I will tell you. Leakage means here, if you see here, whatever, if you see, there will be, all the fields are confined here. Fields are confined inside the cavity here. So there is no leakage, or there is no leakage of fields you can observe from here. So all the fields are confined. Here we have taken S equals to 2D. I think it answers your question. Slot means, we have a slot means you can etch the slot on the top of the SIW cavity to design the SIW slot antenna. Yeah. Yeah. Next question is that
till how much frequency testing facilities is available at your place?
So at my place, we can measure the till 40 gigahertz. So no, 40 gigahertz antenna setup we can measure. For the S parameter, we have till 1 terahertz. 1 tera, that is 1000 gigahertz. Just we have brought.
Can we use that, and how?
So you have to contact the head. Maybe you can collaborate it, and then you can contact the head. Head will give you, or you can contact us, no problem.
The next question is, sir, I am new to this field. Can you make me understand how to read those graphs you should show in slides for RIS, in bracket S11 and phase plot?
Okay. Is it visible?
Yes, sir.
Okay. So now, so if you see the S11, so S11, so we have plotted the magnitude and the phase. So it is how we got, first of all. So let me show you. So this is our unit element. Okay. In unit element, you have to apply the Floquet port. Okay. You have to apply the Floquet port here. Floquet port means generally, because this structure should be means periodic structure, and you have to apply the, that is means just go to the Google Floquet port unit cell simulation. So you will get the now. So what you have to do, you have to launch a power from one port, and you have to get the power from the another. So since this structure is having the metal at the back, so there won't be any transmission. You have only the reflection. So you will get the reflection magnitude and the reflection phase. So reflection magnitude. So here we have plotted the reflection. So you will get this type of graph, that is S11, which comes out to be, that is -2, -3 dB. So this is more clear. So this is for the first frequency S11. This is the S11 for all different other frequencies. This is for the 3.5, 5.1, 5.85, and this one. So if you can observe here, S11 is -2, not more than that. That means S11 is -2. Your entire power is getting reflected back. Power is getting reflected back. Very good. But what is happening? The phase of the signal is getting changed. If it is perfect electric conductor, just a patch is there, then what is going to happen? Then you will have the 90-degree or 180-degree phase will be changed, will be there. But 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 since it is not a perfect electric conductor, it is having some structure which is the diode, some resonant type of structure, so it will change the phase. So you will observe the different phase at different frequencies. Or let's say if I see the black graph, the first one, the black for the black magnitude. So I will have at 3.5 gigahertz, I will have this phase. So numerous phases will be there. So you'll have the different phases will be there. Now, based on that, you study. So whatever we have plotted this one. So magnitude is not responsible, only the phase is responsible. You can observe the for different frequencies, so the phase can be changed. Now you have to choose this type of, you have to choose the particular value of excitation or particular values of particular values of the capacitance to get the particular phase. So in this way, we read the phase diagram. Now, this is used for, let's say, I will just show you. Here it is showing me the phase of, let's say, 0, 90 degree, 0, 45, 90 degree. So it can be used for the design of this RIS surface. So we have not, see in this one, so we have not applied, we have not used any microcontroller. We have just designed the surface. So how we have designed the surface for this one, what, let's say, again the question comes how we got this one. So this we got from the how much, because in the center we don't require any phase change, but as you move away from the center because of the this one, so the beam phase, the phase change is required. So here we require larger number of larger phase at the as you move outer and the so this is very much this is available in the literature. I think it has answered your question. Okay, how much, sir, Z axis, how much distance needed to be, okay. I don't have any idea. Maybe I have not done any simulation. My students are doing. Maybe you can see the literature. Generally, we maybe, okay, maybe I don't have any idea about it because I have not worked upon it. My generally students have worked. Okay, it's lambda by 2. Abhishek is saying.
Yeah. My doubt is if it is lambda by 2 or lambda by 3.
So see, you check it. I don't have any idea. Please get to the. I don't have any idea. I cannot comment on it.
Jafinder will ask, sir, I'm working in antenna from last 15 years. Can we work in collaboration?
Yes, we can work in collaboration. We don't have any problem. Jaswinder, okay, we don't have any problem.
Okay.
Okay, please mail me. I will see that. So what type of work you have done? So what type of work we can collaborate it? No problem. So different DST schemes are there in which we can submit joint proposals and so on.
Okay. I think there is no more doubt, sir. So thank you for delivering a special talk in this FDP. Your insightful presentation and valuable contributions greatly enrich and session are provided the participant with a deeper understanding of the topic, which is SIW antenna, some active and passive RIS, some knowledge of 5G and 6G and some IoT as well. We truly appreciate your time, effort, and willingness to share your expertise with us, sir. Once again, thank you so much, sir, for coming.
Okay. Thank you, Vikram. Thank you. Thanks a lot.
Okay. Participants, this session concludes here. We will now take a lunch break and then our next session will be start at 4 p.m., which is handphone session. Sorry. There is a
11
short,
o'clock.
yeah, there is a short break and then we will continue with 11 a.m. I forgot. Right. Okay, thank you.